The story of quantum computing begins not in modern laboratories, but in the mysterious world of physics. At the start of the 20th century, scientists began to discover that the smallest particles in the universe, electrons, photons, and atoms, did not behave according to the familiar rules of classical physics. Instead, they followed strange laws that seemed to defy logic. An electron could be in two places at once. Light could behave both as a wave and a particle, and observation itself could change reality. This field of study became known as quantum mechanics, and it changed our understanding of the universe forever. For decades, quantum theory remained mostly theoretical, guiding the development of lasers, semiconductors, and atomic clocks. But in the late 20th century, a few visionary scientists began to ask a bold question. What if we could use the bizarre properties of quantum mechanics to process information? That question marked the birth of quantum computing. Unlike traditional computers, which store information in bits that can be either 0 or 1, quantum computers use quantum bits or qubits. A qubit can be both 0 and 1 at the same time, thanks to a property called superposition. Even more powerful is entanglement, a mysterious connection between qubits that allows them to share information instantly, no matter how far apart they are. Together, these principles allow quantum computers to perform complex calculations at speeds that would take classical computers thousands of years. The first quantum algorithms were proposed in the 1980s and 1990s. One of the most famous was developed by mathematician Peter Shor, who showed that a quantum computer could break modern encryption systems in minutes. This discovery shocked the world of cybersecurity and made governments realize the power that quantum technology could hold. By the early 21st century, the dream of quantum computing began to move from the lab into real-world applications. Tech giants like IBM, Google, Microsoft, and startups such as Rigetti and IonQ entered the race. In 2019, Google announced that its quantum processor, named Sycamore, had achieved quantum supremacy, performing a calculation that would take the world's fastest supercomputer thousands of years. Though some debated the claim, the achievement symbolized how far the field had come. To understand the true power of quantum computing, imagine trying to solve a maze. A classical computer explores each path one by one, checking which way leads to the exit. A quantum computer, using superposition, can explore all possible paths simultaneously. This parallelism makes it extraordinarily fast at solving certain types of problems, especially those involving huge amounts of data or complex probabilities. Quantum computing holds promise for industries across the world. In medicine, it could simulate molecular interactions with incredible precision, speeding up drug discovery and helping to design personalized treatments. In finance, it could analyze global markets, optimizing portfolios and predicting risks more accurately than ever. In logistics, it could plan the most efficient routes for thousands of vehicles, reducing fuel waste and delivery times. In climate science, it could model atmospheric systems in detail too complex for any traditional computer, leading to better predictions and solutions for global warming. However, power always comes with responsibility. The same quantum algorithms that can improve cybersecurity could also destroy it. Modern encryption methods depend on the fact that factoring large numbers takes enormous time for classical computers. Quantum computers could break these systems easily, exposing sensitive data worldwide. As quantum computing continues to evolve, its future feels both thrilling and uncertain. We stand on the edge of a new scientific era, one where machines may solve problems too complex for the human brain to imagine. Yet, with such power comes a moral question. How will we use it? Will quantum computing lead to a new age of understanding? Or will it deepen inequality between those who control technology and those who do not? Some scientists believe quantum computing will complement, not replace, classical computing. Quantum machines excel at solving specific problems, like optimization, simulation, or encryption, but they are not ideal for every task. The real future may lie in hybrid systems, where quantum and classical computers work together, combining speed with stability. Education will play a vital role in this transition. A new generation of engineers, mathematicians, and philosophers will need to understand quantum theory not only as a science but as a language of thought. Schools and universities around the world are introducing quantum programming and ethics into their curriculums. The ability to think quantum, to embrace uncertainty and probability, may become as essential as reading or writing in the digital age. Quantum computing also raises profound philosophical questions about reality itself. If particles can exist in multiple states at once until observed, what does that say about the nature of truth? Are there infinite realities existing side by side, each shaped by different choices and observations? Quantum mechanics reminds us that certainty is an illusion, that knowledge is a wave constantly collapsing into new possibilities.